everyone, welcome to this explainer. Today, we're jumping straight into what I think is a genuine cosmic detective story. We're going to challenge our fundamental understanding of the universe's most elusive substance, dark matter. It's omnipresent, it shapes our galaxies, it dictates how they move, and yet, it stubbornly refuses to be seen. But what if the way we've been thinking about it for decades is just fundamentally incomplete? With an incredible flood of new data pouring in from cutting-edge telescopes, we're finally getting a closer look at the hidden architecture of the universe. So get ready, because we're about to explore some groundbreaking research that might just rewrite the astrophysical rulebook.
All right, here's our roadmap for today. We'll start by questioning the classic model of dark matter. Then we'll unpack the self-interacting hypothesis. After that, we'll test this new idea against three major cosmic mysteries. And finally, we'll ask the big question, are we moving toward a brand new paradigm?
Okay, part one, questioning the classic model.
For decades, the textbook answer has been that the dominant classic model assumes dark matter is cold and collisionless. In astrophysics, cold basically means the particles aren't zipping around at light speed, and collisionless means they have almost zero interaction. They're thought to act like ghosts, just passing right through each other, never interacting, never colliding. But here's the catch. Recent observations show that certain structures, specifically the dense centers of dwarf galaxies and galaxy cluster cores, are simply way too dense to be explained by this old framework. If dark matter truly never interacted, these incredibly dense central clumps just shouldn't exist. It's a headache physicists call the core cusp problem. So we really needed a new idea.
Which brings us right to part two, self-interacting dark matter. Enter physicist Haibo Yu from UC Riverside. He published a fascinating paper in Physical Review Letters proposing a massive conceptual shift. He basically asked, what if dark matter is actually dynamic? What if, instead of acting like ghosts, these particles actually bump into each other, collide, and exchange energy, completely hidden away in their own dark sector? It sounds like a simple tweak, but it profoundly changes how we understand the internal thermodynamics and the sheer structure of the vast dark matter envelopes surrounding our galaxies.
When these dark matter particles collide and exchange energy, it triggers a really wild phenomenon known as gravothermal collapse. Let's think about the thermodynamics for a second. In a standard, non-interacting halo, particles just orbit freely. But if they can scatter off each other, they start transporting heat from the hotter, denser inner regions of the halo out to the cooler edges. Now here is where it gets strange. As the core loses heat, it paradoxically contracts and heats up even more. It operates as a system with negative heat capacity. Eventually, the central region just falls inward on itself, concentrating into an insanely dense, highly compact core. So this mechanism works in 4 specific steps. 1, the dark matter particles collide. 2, they transfer thermal kinetic energy during those crashes. 3, that outward heat transfer triggers the gravothermal collapse, rapidly packing matter into the center. And 4, this is the crazy part. Each of these dense, invisible clumps can reach a localized mass equivalent to 1 million of our suns. It creates this absolute behemoth of a gravitational anchor, completely invisible to our telescopes, just lurking within the broader dark matter halo.
All right, part 3. Let's see how this solves 3 major cosmic mysteries.
Our first clue is way out in the deep cosmos, in a distant, warped galaxy known as JVAS B1938+666. This whole system acts as a gravitational lens, meaning the immense gravity of a foreground object is severely bending and magnifying the light of a background galaxy. But the specific visual distortion we're observing here, it just doesn't add up under the old collisionless rules. When astrophysicists calculate the mass-to-light ratio needed to produce this exact warp, there's a glaring discrepancy. There simply isn't enough visible matter to cause a bend the sharp, and a standard diffuse dark matter halo wouldn't produce such a highly localized pinpoint perturbation.
When we analyze that very specific anomaly, it completely gives away the presence of a massive, super dense object that we simply can't detect directly. It's bending the light sharply, but the culprit is totally invisible. This compact gravitational signature is incredibly hard to reconcile with the old dark matter model, which predicts much smoother, puffier halos. But guess what? This exact density profile perfectly matches the mathematical footprint of a tightly wound core created by gravothermal collapse.
Our second case brings us a lot closer to home, the GD1 stellar stream, located right here in our own Milky Way. If you're not familiar, a stellar stream is essentially a delicate ribbon of stars moving together through space, usually the leftovers of a dwarf galaxy or star cluster that got stretched out by the Milky Way's gravity. But astronomers noticed a really bizarre structural flaw in GD1. It has this distinct notch and a spur where stars have been dragged completely out of their expected alignment.
Imagine a bullet ripping straight through a stream of water. Researchers believe that one of these massive, invisible dark matter cores violently crashed right through the GD1 stellar stream. Because this dark matter core packs the mass of 1,000,000 suns into such a tiny volume, it left behind a pristine, clear gravitational footprint. As it plowed through, its intense gravity violently yanked nearby stars out of their orbital lanes, scattering them into that precise notch and spur pattern, before continuing unseen on its path through the galactic halo. Finally, Case 3 takes us to our galactic neighbor, the Fornax dwarf satellite galaxy. Inside this galaxy is a specific star cluster called Fornax 6. The big mystery here is its extreme compacity. Based on standard physics, the stars in Fornax 6 are grouped way more tightly than they should be. Over billions of years, tidal forces and internal collisions should have caused this cluster to expand and eventually dissolve into the broader galaxy. Yet something is holding them together in a strangely tight embrace.
Under the dynamic dark matter model, it makes perfect sense. A super dense core sitting at the center of Fornax 6 acts exactly like an invisible snare, creating a powerful gravitational trap. As stars pass near or through this dense central region, the localized pull is so intense that it actually captures them, pulling them into this unusually compact formation. The invisible core is basically serving as a permanent gravitational anchor, locking those stars together way past the point when standard physics says they should have drifted apart.
Which brings us to our final section. Are we heading toward a new paradigm?
The true beauty of this hypothesis is its incredible unity. Just think about it. We have three totally distant phenomena: a distorted lens billions of light years away, a ripped stellar stream right here in our own galaxy, and a trapped star cluster next door. We're looking at three completely different cosmic scales, yet one single physical mechanism, self-interacting dark matter undergoing gravothermal collapse, perfectly explains the root cause for all of them.
So, let's summarize the key takeaways here. First, this theory beautifully unifies previously isolated cosmic mysteries. Second, the specific densities we measure in these anomalies match the exact predictions of self-interacting dark matter cores perfectly. Now, to be clear, this doesn't mean we're completely throwing the dominant cold dark matter model in the trash just yet. Science takes rigorous peer review and extensive testing. But it does provide incredibly coherent answers where we previously just had frustrating anomalies. And most importantly, it gives astronomers a crystal clear path for testing future data, specifically looking for these compact cores using tools like the Euclid or James Webb Space Telescopes. With these next-generation telescopes coming online, we're about to be flooded with unprecedented high-resolution cosmic data. So I'll leave you to ponder this. As we gather that new data, are we standing on the brink of a total revolution in how we understand the very scaffolding of our universe? Is dark matter, the invisible architect of the cosmos, actually far more dynamic, interactive, and forceful than we ever dared to imagine? Thank you so much for joining me on this explainer. Keep your eyes on the stars.